Hello everybody, this is Dr. Schleith, and in this video I'll be going over the learning objectives associated with work, energy, and power. As usual, please remember to keep a record of all of your work in a journal and send me pictures of your journal pages by noon Friday each week. Alright, who could explain the significance of this next slide? Mr. Kilogram saw a kangaroo man captured. If you can explain the significance of that, leave it in the comments below. All right, so the learning outcomes associated with work, energy, and power are students will be able to give examples of conversions of energy between different forms. One of my sort of favorite things to do, try to trace the energy, the light that's coming from your computer screen. Try to trace where did that energy sort of come from, and try to go back as sort of far as you can. So you might think, well, it's there's a battery or it's plugged in, and so energy that's coming out of the wall, where's that coming from? And it might be a power plant nearby that's burning fossil fuels. And if you think about where did the fossil fuels get their energy from, the earth turned these plants and animals into these fossil fuels, but these were organisms that may have lived during the Carboniferous period 440 million years ago when plants were photosynthesizing sunlight just like they are today. And so it's really solar energy ultimately that's, powering that. Kind of cool to think about. Students will be able to understand and use the concept of work. Students will be able to apply the principle of conservation of energy to simple examples involving energy in different forms. And so those simple examples will be kind of like the pendulum that we've been working with our lab work, right? We're converting the potential energy as we move the pendulum up in Earth's gravity field. It has potential energy, but then as it swings, it picks up speed, and so that's kinetic energy of motion. Students will be able to derive and use the formula for kinetic energy and potential energy, and students will be able to define and use the equation for power. Let's start with the concept of work. Students will be able to understand and use the concept of work. And so what is kind of the definition of work here? Well, work is the dot product or the scalar product of force and displacement. So we can multiply the two vectors, force and displacement, and get a scalar quantity like work. So work and energy are scalar quantities, and they're both measured in joules. Only the component of force, though, that acts in the direction of displacement contributes to the work done. So we can kind of capture that with the equation work equals force times displacement times cosine theta, where theta is the smallest angle between those vectors. Or force cosine theta times displacement. That kind of makes a little bit more sense when you think about force times cosine theta. That kind of is the component of force that's going in the direction of displacement. The units of work are Newton meters or joules, but what are the base units of work? Let's think through that. So because work is force times displacement, we know that force is measured in newtons and displacement is measured in meters. But a newton is not a base unit. So recall from Newton's second law that a newton of force is equal to a kilogram of mass times a meter per second squared of acceleration. So if the base units of a newton of force are kilogram meters per second squared, and then we multiply it by meters of displacement to get work, then that makes the base units of work kilogram meters squared per second squared. So a joule is really a kilogram meters squared per second squared. Those are the base units of work. An expanding gas can do work, right? And so it could be work either done sort of to a gas, so we can compress a gas, right? And we're doing work to compress the gas, or the gas could sort of do work by expanding. And so the work done either on or by a gas is equal to the pressure times the change in volume. Show using base units that the equation is homogeneous. And so we need to make sure that we have the same units on the left side as the right side of this equation for it to be valid. Let's take a moment to work through that. Just a minute ago, we said that work has base units of kilogram meters squared per second squared. All right, so those are the base units of energy. Now pressure is force per area. It's the force per area. So remember that the base units of force are kilogram meters per second squared. A Newton is a kilogram meter per second squared. Right? That's sort of where we began to get this. So pressure is force per area. So here I just have force, and so the units of area in the denominator are meters squared. Length times width for area, and each one of those linear dimensions, length and width, would be measured in meters. And so if we think about what's going to cancel here, this meter in the numerator would cancel out one of those meters in the denominator, and the base units of pressure we have now are kilogram per second squared per meter. Right? So a kilogram per meter per second squared, those are the base units of pressure. But we still need to multiply the units of pressure by the units of volume to see if we've got homogeneity in our equation. Because volume is length times width times height, and each one of those would be measured in meters, the length, width, and height, then the units of volume are meters cubed. So we still had a meter left over in the denominator here, and now we can see that that's going to cancel one of the meters in the numerator, and we're left with meters squared. So indeed, we can see that we've got kilogram meters squared per second squared on the right side, which is equal to kilogram meters squared per second squared on the left. So work has the same units as the product of pressure and change in volume. By showing that the units work, we don't really prove the validity of the equation, but if the units didn't work, it would disprove it. Work and energy, both measured in joules. Here's a portrait of James Joule, and energy could be defined as the ability to do work, but I think it's a little bit more complicated than just that definition. Here we see Joule's apparatus for measuring the mechanical equivalent of heat. And let me get rid of that writing there so you can better see it. And maybe if you studied that figure there for a moment, you'd be able to come up with some reasonable hypotheses about what exactly Joule was doing with this sort of apparatus here. I leave it to you to either think about that on your own or research it if you're curious enough. Potential energy, sometimes the letter U is used to represent that. It's the ability of an object to do work as a result of its position or shape. And so here there's a boulder up on a cliff, and it has potential energy because of its position in Earth's gravity field. It has the potential to sort of fall this vertical distance, the height. The spring has potential energy due to its shape because somebody has compressed the spring there. The spring now has energy stored inside of it. We call that strain potential energy stored in objects which have had their shape changed elastically. Chemical potential energy is energy stored in chemical bonds, and so there's also a form of potential energy, chemical potential energy. And gravitational potential energy results from gravity's potential to do work on massive objects that are separated by some distance. So here, near the surface of the Earth, we use the equation mgh to calculate the potential energy due to gravity. That equation is actually derived from the definition of work. And if you click on the link here, you'll be able to see where I've derived the equations for potential energy due to gravity and kinetic energy. And that video really corresponds with the learning objective that you read here, the fourth bullet point. Students will be able to derive and use the formula for kinetic energy and potential energy. So make sure you either finish watching this video and then take a look at that one for the derivation of these equations, or take a moment to view them now and then come on back and finish. Kinetic energy is associated with mass and speed, and its equation is 1/2 mv squared. And again, that equation, where it comes from, is derived in the video. It comes from Newton's second law, the definition of acceleration, and the definition of work. And work does indeed equal the change in kinetic energy. Work kinetic energy theorem is an incredibly useful theorem when we think about objects can't just change their kinetic energy, right? Because energy is neither created nor destroyed. So if an object, objects can't just change their kinetic energy on their own without any work being done to them or without any energy being expended. So anytime there's a change in kinetic energy, there must be some energy spent, some work done to cause that change in kinetic energy. And those two things are equal. Work equals the change in kinetic energy. Hooke's law describes the force in a spring. We first introduced it when we looked in the dynamics chapter at different types of forces. And as we study energy now, we can think about the strain energy, the potential energy stored inside of a spring. So keep in mind that Hooke's law says that the force of a spring is equal to the spring constant K times the displacement x. The negative sign here just indicates that if you stretch a spring out, the force is always opposing the direction of the displacement. So if you compress a spring, if you sort of push the displacement this way to compress the spring, well, the force wants to oppose it and act against it. So K is a constant known as the elastic constant or the spring constant, and it's measured in newtons per meter. When springs are stretched and they return to their original length, we call that change elastic, an elastic change. When a spring is stretched beyond the point of elasticity, called the elastic limit, the spring will permanently deform, and the change is called plastic. So you could have an elastic or a plastic deformation. Elastic strain energy is the area under a force extension graph. So you can imagine if we plotted force against extension for a spring. So as we apply force to a spring, we stretch it out longer and longer, right? The extension is greater and greater. And if we were to take the area underneath this plot, we'd have 1/2 base times height, or 1/2 force times extension. And that would give us the work done, which is equal to the energy stored in the spring. So the work we do in stretching out a spring is equal to the energy stored in that spring, because energy is conserved. And we're sort of neglecting any energy losses that might have sort of occurred there. Strain energy is energy stored in a body due to its shape. And so an equivalent way to express the equation 1/2 force times extension, which is the area underneath this graph here, would be if we used Hooke's law and we substituted in kx for force. Then we would have the equation that you're reading right here, 1/2 kx squared. So we could either think about the strain energy as 1/2 force times extension, if we call this extension x, or 1/2 kx squared. Two equations for elastic strain energy. Important to have in your notes, certainly. The energy or the work is in joules if K is in newtons per meter, and x, the extension, which is the same as the change in length, is in meters. Young modulus we'll spend a little bit more time studying in a subsequent chapter, but for now, let's just get some definitions down in our journal. And we've actually seen young modulus in at least one previous worked example with base units. So young modulus, E, is the stress over the strain, and stress is force per area. So it's the same as the units of pressure, newtons per meter squared. Strain is a ratio of an extension to the original length of an object. And so it's sort of like how much does the object get elongated compared to its original length. So sometimes we can call that delta L over L, the change in length divided by the original length, the ratio of two lengths. So it doesn't have a unit, and we use the Greek letter epsilon for strain. Stress, we use the Greek letter sigma, and again, it's force per area. And Young modulus is the ratio of those two, stress divided by strain. So sigma over epsilon is Young modulus, stress over strain. Because strain is dimensionless and itself doesn't have any units, then the units for Young modulus are the same as the units of stress, which are sort of in the denominator or in the numerator here. Right? So Young modulus has the same units as stress. Sometimes we'll see this equation for Young modulus, E would equal force times the original length over the area times the extension. And this is just sort of plugging in these quantities for stress and these quantities for strain in this equation. So sometimes we may be given sort of, 4 pieces of information like this and asked to calculate the Young modulus, and you could just remember that Young modulus would be equal to force times original length divided by area times extension. It's like the denominator of the denominator, right? The original length here ends up back in the numerator because we're dividing by strain. Take a moment to work with those equations until you can kind of prove that to yourself. Oh yeah, if I substitute everything in here, I should end up getting this flax for Young modulus, FL over AX, where X is the extension, A is the area, L is the original length, and F is the force. Here's a table of different forms of energy, because we know that energy can neither be created nor destroyed, but only converted from one form to another. We could sort of classify all forms of energy as either a type of potential energy, due to position or shape, or a type of energy of movement, of motion. Kinetic energy. So strain energy is an example of potential energy, right, due to the sort of changing the shape of an object, like the spring that we mentioned. Electrical energy is energy associated with moving electric charge. So because those charges are moving, there's a current, a flow of charge. That would be an example of kinetic energy, electrical energy. Sound energy is a mixture of potential and kinetic energy of particles in a sort of like a pressure wave. So, sound energy being propagated through air or water or something. Wind energy is kinetic energy of air. Light energy, energy of electromagnetic waves. Solar energy is a mixture of light and heat energy from the sun. You also have like the nuclear energy that sort of powers the sun, right? So there's an energy conversion there. Let's see, our sun has a power of about 4 by 10 to the 26 watts, I believe. So nuclear energy, energy associated with particles in the nuclei of atoms. Chemical energy, those are more about like the electrons on the outside, actually transferring electrons, the chemical bonds. And then thermal energy, heat energy. And this is an incomplete list. There are many different forms of energy that exist in nature. And the discovery of different forms of energy, like mass energy equivalents, some of the greatest leaps forward in terms of our understanding of the universe and physics. The idea of efficiency is also important in physics. So efficiency is either the useful work done divided by the total energy input, or the useful power out divided by the total power in. So we could think about efficiency as either in terms of work or power. Power is just the rate at which energy is done. So if we think about, what's the useful work that's being done divided by the total energy that went into it, the efficiency is really telling us kind of like how good of a job the energy conversion that took place, occurred. Was there any energy losses? So processes are never 100% efficient. And we certainly couldn't have anything where we got more sort of useful work out of something than the energy that we put in. That would sort of violate a fundamental law of thermodynamics, that idea that energy is neither created nor destroyed. We would be like creating energy out of nowhere if we got more energy out than we sort of put in. So there was one episode of The Simpsons where I think school got canceled and Lisa was trying to stay busy, and so she was working on this problem and, wouldn't you know, invented this perpetual motion machine that Homer makes an observation here. It just keeps going faster and faster. Young lady, in this house, we obey the laws of thermodynamics. And so, you can't just violate the laws of thermodynamics, in the universe or in the Simpsons household. So Homer wasn't too pleased that Lisa decided to violate that important law of thermodynamics by inventing this perpetual motion machine. But you can go ahead and try if you like. Anytime there may be a claim of a perpetual motion machine, scientists would be very, very careful about that, and they'd be looking for that source of energy that may not be obvious. What's actually powering this thing? Because we're not so quick to accept a violation of a fundamental law, but indeed, maybe there is an exception to that law. We just haven't observed it yet. Thermal energy. So here's an equation for sort of like the thermal energy, the heat energy that's supplied to something, equal to the mass times the specific heat capacity times the change in temperature. So it's really a way to think about this quantity, specific heat capacity, that tells us how much energy is needed to raise the temperature 1 kilogram of this substance 1 degree, Kelvin. And different substances have different specific heat capacities. I always like to think that, when you go to the beach and it's a hot sunny day and you forget your flip-flops, the sand burns your feet really badly because the specific heat capacity of sand is so low that even though there's the same amount of thermal energy from the sun incident upon both the sand and the water feels so much cooler on your feet because its specific heat capacity is so high that it takes a lot of energy to raise the temperature of water, but not so much energy to raise the temperature of the sand. And so the sand feels very hot on your feet while the water is very cool, even though the same amount of energy is incident upon both of those things. In this slide, it asks us, what is the unit of specific heat capacity? And then the answer is sort of given right there. Now, note that these are not base units, but the units here should make a lot of sense to you when we think about if the left side of this equation has units of joules, because it's energy, right? Thermal energy, Q. So joules, then we need to have joules on the right side. Because specific heat capacity has joules in its numerator, that's sort of, how we say it's the amount of energy or the number of joules, but it's per kilogram, right? So per unit mass per degree Kelvin. And that's why we need to have units per degree kilogram, per degree Kelvin in the denominator to cancel out the units of mass and temperature. I'll leave it to you to work through what are the base units of specific heat capacity, and leave it down in the comments below. Watt is the unit of power. So power is the rate at which work is done, or the rate at which energy is converted or transferred. And we measure power in watts. An alternative equation for power is force times velocity. And so if we think through the idea that work divided by time is power, but previously we've said that work is force times displacement, then when we consider work over time as force times displacement divided by time, we know that displacement divided by time is velocity. And so sometimes it's easier to make sense of a calculation for power by considering force times velocity, which is just an alternative expression for power, as we can derive here. Here we see an illustration of James Watt, in his laboratory, keenly observing one of his experiments. All right, and for lab day, certainly Principal Skinner's right here. Science has it all. This episode of Bart's Comet, Principal Skinner says, you get all the fun of sitting still, paying attention, being quiet, writing things down. Yep, science has it all. We know that for our lab day. So this week we're going to be looking at a friction lab, measuring the coefficient of friction between two surfaces. And the lab kind of goes like this. As I vary the weight of a block, I will measure the force required to pull it along at constant velocity. So really we're going to add weight on top of a block, and then we're going to pull it with a spring scale, and the spring scale, or Newton meter, is a way to just measure the force. Now we're going to consider now that the weight is going to equal the normal force. So the weight acting down will be balanced by the normal force acting up. And the strength with which we pull the block across, the force that we pull it with, will equal the frictional force acting against it, because we're going to pull the block with constant velocity. Constant velocity means no acceleration, and no acceleration means the net force is zero. So even though we're supplying a force in one direction, there must be an opposing force with the same magnitude acting against it, because there's no acceleration. You can think about it like this. If we pull a block along, the moment that we pull it, we've set it in motion. So we shouldn't need to continue pulling it. It should just be an object in motion that would remain in motion. And the fact that it doesn't keep moving, that as soon as we let go of it, it comes to a stop, well, that's because not of the absence of our pull force, but due to the presence of some other force, namely the friction force. So by pulling something along at constant velocity, what we're doing is we're really just matching the friction that's acting against our pull force. And so we're indirectly measuring friction when we pull the block along at constant velocity. Friction is somewhat poorly understood, but the equation that sort of governs friction is that the frictional force is equal to this coefficient of friction, some number that sort of describes how slippery or slick the surfaces are, times the normal force. Let's see that. Here's a free body diagram of those forces that are acting on our block. So again, we're going to add weight to the block. So we're going to be varying the weight W and therefore the normal force, because whatever weight we supply, the table will exert adequate normal force up to balance it. Hopefully we won't add so much weight that we overwhelm the structural integrity of our lab bench there. But indeed, that's sort of the idea that whatever weight that we put on the table, as long as the table is strong enough, it will supply enough normal force to balance the weight out, because the object isn't going to be accelerating, hopefully, in the y direction. We don't want the table to break, then it will accelerate right down. The applied force here pulling to the right, that's the thing that we're going to measure with our spring scale. But remember, we're indirectly measuring the frictional force that's opposing it, because those forces must be in balance if we pull it along at constant velocity. We're trusting Newton's second law here that the net force on an object is equal to mass times acceleration. And if we can observe that there's no acceleration because we're pulling it along at a constant speed, then we know with whatever force we can measure on our spring scale, on our Newton meter as a pull force, is really also equal to the frictional force that's acting against it. So the equation that I mentioned a moment ago is that the force of friction equals mu, the coefficient of friction, times the normal force. And if we think about the equation of a line, y equals mx, then for our lab work, we're going to make a plot of the frictional force against the normal force. And theory suggests that as we increase the weight, the normal force will increase. You can kind of imagine intuitively, it's harder to pull something along, sort of the heavier that it is. And you can kind of make sense of that as, we're sort of pushing those surfaces together tighter, and friction is kind of like the rubbing of all of the sort of, at the atomic scale, how sort of rough those even seemingly smooth surfaces are, right? So there's sort of all the ridges and bumps and divots and things as two surfaces rub past each other, they sort of catch, and that's kind of what friction is. And so as we add more weight, those surfaces are pressing together even tighter, and so we'd expect the frictional force to be greater as we increase the weight and therefore the normal force. So there will be a trend line that we can sort of plot our data on. We can plot our data on a set of coordinate axes, and the data should fall into a trend that we can then draw a best fit line through. Remember to scale your axes reasonably. Here we're plotting the frictional force measured in newtons on the y-axis against the normal force, also measured in newtons on the x-axis. Try to collect 7 data points, and then draw a best fit line through the data. And find points on your best fit line which intersect the gridding of the graph paper, like these points here. And then we can read off the coordinates and do a slope calculation. There are a few students that are still calculating the slope with data points, and we really want to avoid doing that if we can, because the trend line is more accurate than any 2 data points. We would only need to collect 2 data points if we were just going to calculate the slope with 2 data points. So by seeing a best fit line that represents a trend in a lot of data, we're getting a more accurate answer. There will be a bonus lab this week where we're going to measure the force to open the door as per our explanation of moment of force last week. So as we vary the distance from the pivot to push open the door, we're going to measure the force required to open that door. And so we'll be measuring how much force it takes to open the door very close to the hinge, and how much force it takes to open the door where like the door handle is far away from the hinge. And as theory suggests, the reason why we put door handles far away from the hinge is because minimal force is required there, where we maximize our distance to the pivot. And so we should be able to determine the moment of force to open the door by plotting a graph of the force required against 1 over the distance to the pivot. And you guys are lucky enough to get a double bonus lab this week where If you click on the video link, I'm going to show you how we can calculate the coefficient of friction theoretically, and then we'll be able to check that with a quick measurement that we can make in the lab, same time that we do our other friction lab this week. So, thanks for watching. I'll see you next time.